All right, let's get into it. It's pretty wild how sometimes the simplest rules in physics can explain the most massive, mind-blowing things about our planet. And today we're talking about a big one, a story all about sinking, floating, and believe it or not, survival. So let's start with a huge puzzle literally right under our feet. Why is our planet built the way it is? I mean, it's not just a big random ball of stuff, right? It's organized, layered, with all the really heavy material like iron and nickel packed down deep in the core. So how on earth did it get that way? Okay, now for puzzle number 2, let's go to the complete opposite extreme, the coldest places you can imagine. We're talking Antarctica, minus 50 degrees Celsius. At that temperature, you would think a lake would just freeze solid, top to bottom, a giant block of ice. But it doesn't. Life actually survives, thrives, in liquid water underneath the ice. How in the world is that possible? So here's the really cool part. You've got these two totally different questions, one about the planet's formation, the other about life in the Arctic, and they seem to have nothing in common. But get this, they share the exact same answer. And that answer is hidden in the physics of fluids. All right, so to solve these two big mysteries, we need to get on the same page about a few things first. Let's start with the absolute basics. What exactly is a fluid? So when you think about it, what's the real difference? Well, in a solid, all the molecules are kind of locked in place, in this rigid grid. That's why a rock has a fixed shape. But with fluids, and remember, that means liquids and gases, the molecules are free to move around and slide past each other. And that ability to move is what gives them their most important property. They can flow. But why? Why can they flow? Well, it's all about a tiny battle happening at the molecular level. See, in solids, the attraction between molecules wins. It's like they're all holding hands really, really tightly. But in fluids, the molecules have more energy. Think of it as thermal energy. They're jiggling and bouncing around like crazy. And all that movement is just strong enough to overcome that sticky attraction, letting them break free and just tumble past each other. Okay, so we've got fluids down. Now let's bring in the real star of the show, the concept that's going to solve everything for us: density. Density sounds technical, but it's actually super simple. It's just a measure of how much stuff is packed into a certain space. How crowded is it? Are the molecules all jammed in there shoulder to shoulder, or do they have a lot of room to spread out? That's all density is. To put this into perspective, let's look at a few examples. Air, is not very dense at all. Its molecules are super spread out. Then there's water, which we kind of use as our baseline. We say its density is 1. But then you have something like solid iron, which is almost 8 times denser. That means it's packing way more mass into the same amount of space. This comparison is going to be really important. Okay, one more key thing about fluids. Even though liquids and gases both flow, they do not behave the same way when you try to squeeze them. Gases are compressible, you can pack them into a smaller space. Liquids, not so much. Think about this. It's the perfect example. If you take a syringe, pull in some air, and then plug the end with your finger, you can easily push the plunger down, right? You're compressing the air. But now, try doing the exact same thing with water. Fill it up, plug the end, and push. The plunger barely moves an inch. For all intents and purposes, liquids like water are incompressible. Okay, we've got our tools ready, we understand fluids, and we get density. Now for the one simple rule that brings it all together. And honestly, it's so simple, it's beautiful. Here it is. When you mix a bunch of stuff together, gravity's gonna pull on everything. But the stuff that's more dense is gonna get pulled down harder, and it's gonna sink. The less dense stuff, it basically gets pushed up and out of the way, so it floats. That's the whole game right there. Denser things sink, less dense things float. And you see this everywhere. Oil on water, oil is less dense, so it floats. Drop an iron bolt in that water, it's way denser, so it sinks. A helium balloon, it rises because helium is way less dense than the air around it. And here's a little clue for our second puzzle. Ice floats on water. Why? Because it's less dense. Just tuck that little fact away for later. All right, we've got our concepts, we've got our rule. Let's go solve that first mystery. Why is the Earth built like a layer cake? So picture this. Billions of years ago, the early Earth was just this giant swirling ball of hot, molten rock. It was basically a planet-sized fluid. And in that massive planetary soup, gravity started doing its thing. All the super dense stuff, remember that iron and nickel? It started sinking, pulled straight towards the center. And all the lighter, less dense materials, things like silicates, they got pushed outwards, floating up to the top. Eventually, that top layer cooled and hardened into the crust we live on. And there you have it. The planet sorted itself out perfectly, all based on density. First puzzle solved. Okay, one mystery down, one to go. But this next one, this one's a little different. It's got a twist. To figure out how life survives under the ice, we have to look at how water is a total weirdo and seems to break the normal rules of density. You know, with almost everything else, the logic is really straightforward. You cool something down, its molecules slow down, they huddle closer together, and the whole thing gets denser. Simple. But water? Oh no, water is a total rebel. It plays by its own rules. And here's the key to the whole thing. It all comes down to a single magic number: 4 degrees Celsius. As you cool water down, it does get denser, just like you'd expect, but only until it hits 4 degrees. At that exact point, water reaches its absolute maximum density. It can't get any more crowded. Okay, so let's walk through what happens in that Antarctic lake. The freezing air starts cooling the water at the surface. As that water cools down towards 4 degrees, it gets denser, so it sinks. And that pushes the slightly warmer water from below up to the surface. You get this constant cycling, this turnover. And it keeps going until the entire lake, top to bottom, is at a uniform 4 degrees Celsius, peak density. But now the magic happens. As the surface water gets even colder, say 3 degrees, then 2, then 1, it actually becomes less dense. So what does it do? It floats. It stays right there on top. This super cold, less dense layer forms on the surface, and it's that layer that eventually freezes solid. And that sheet of ice on top acts like a perfect blanket, insulating the massive pool of 4-degree water underneath from the ridiculously cold air above. And that's the whole secret. It's this one incredible, bizarre, rule-breaking property of water that makes life possible in the coldest places on Earth. It allows entire ecosystems to just ride out the winter, totally safe in their relatively cozy 4-degree liquid world, while a blizzard rages just a few feet above them. So, from the formation of our entire planet to a single fish surviving under the ice, it all comes back to the same simple physics of sinking and floating. It really makes you think, doesn't it? What other absolutely huge, world-shaping secrets are hiding in plain sight, just waiting to be discovered in the simple rules of the world around us?